Hi there, this Bars Lab here. So it's been a very busy month of this new year, but now I finally have some more time to make more videos. So I'm going to start this new year with the following question, whether or not Professor Lewin actually did manipulate the weights of his cards in his elastic collision experiments. So in this particular experiment, there was the argument that the small mass card actually weighs more than they say it is, right? So the given weight of card 1 is 241 grams, and of card 2 is 482 grams. So there are supposed to be a 1-to-2 mass ratio, but yes, on a small card we can see a blob of clay. So a certain amount of mass has been attached to it. So the mass of card 1 has been increased with a certain amount because of the piece of clay. Now also there is a bunch of stuff on card 1, and therefore card 2 should have twice as much stuff on it in order for it to weigh twice as much. So the argument is that card 1 actually weighs more than it is because the results cannot be true according to the alternative model, according to draft science model. Card 1 must weigh more. So let's take a look. I have done some calculations. I have a bunch of columns. The first column gives us the mass of card 1. The second column gives us the mass of card 2. The third column gives us the length of the flag that will pass through the photogate. The next column gives us the timings of card 1 coming through photogate 1. So these numbers. So let's assume that these numbers are correct, that the timings are correct, okay? So we have 0.123, 0.186, and 0.375 over here. So timing 1 is 0.123, and then the next timing is the reflection of card 1, 0.375 seconds, and then the next one is card 2 going through photogate 2, which is 1.86 seconds. Then in the next one, we have the velocity of card 1, the velocity of card 1 bouncing back, the velocity of card 2, the initial momentum before collision, the total amount of initial momentum before collision, then the momentum of card 1 bouncing back, the momentum of card 2, and then the total amount of momentum if we treat momentum as a scalar. So this is the total amount of momentum after collision. So card 2 going that way and card 1 bouncing back. If we treat them as a vector, we would have to subtract them, and that would give us the total amount of momentum before collision. And then in the next column, we have momentum, the total amount of momentum if we treat it as a scalar. So this is according to the draft science model. Direction does not matter. We always have to add the momentum as with a positive value. So in the first case, let's assume that Professor Lewin is not lying, that card 1 is actually both cards have a 1-to-2 mass ratio. So you have 2.41 kilograms versus 0.482 kilograms, and that will give us a total amount of momentum before collision of 1.95. And if we treat it as a vector, so then after collision, we would have a total momentum of 0.194. So 0.95 versus 0.194, very close numbers. They match almost perfectly. Only 0.001 difference. So momentum is conserved according to conventional science. According to draft science model, we would have a total amount of momentum after collision of 0.323. So 0.195 versus 0.323, which is a lot more momentum after collision than the initial amount of momentum. So this is a insane free momentum experiment. So now let's increase the mass of card 1 let's increase it to 350 grams instead of 241 grams. then we will get a total amount of momentum before collision of 0.84. Now, after collision, if we treat it as a scalar, if we treat momentum as a scalar, the total amount of momentum is 0.352. So 0.284 versus 0.352. We still have too much momentum. This is still a free momentum experiment. So we still have to increase the mass of cart 1. So let's say it weighs 400 grams. Then we have a total initial momentum before collision of 0.325. And then after collision, if we treat it as a scalar, we have a total momentum of 0.365. So 0.325 versus 0.365, still too much momentum. So we still have to increase the mass of cart 1. So now let's say it weighs 450 grams. Then we have a total initial momentum of 0.365. After collision, if we treat it as a scalar, we have 0.379. So 0.365 versus 0.379. Still 0.12 too much. Or yeah, 0.12 too much. Still a little bit too much momentum. Maybe this could be an acceptable error range, but the error range for conventional science, and if we assume that Professor Lewin is not lying about the weights, then the difference in error between momentum before collision and momentum after collision is only 0.001. So now let's start to increase the mass of cart 1 until the difference between momentum before collision and momentum after collision, right, according to Draftsman's model. Let's start to increase the mass until the difference is also only 0.001. Right, so we still have too much momentum. Let's increase the mass of cart 1 to 460 grams. Then the total initial momentum is 0.373, and the momentum after collision is 0.381. So we still have 0.09 too much. Okay, could be an acceptable error range. Let's increase it to 0.470. Then the initial momentum before collision is 0.382, and after collision, if we treat it as a scalar, is 0.384. So now the difference is only 0.002. So now we're getting, so this is an acceptable error difference. If we want to be perfect, all right, then we would have to increase the mass to 474 grams. Then the difference between the initial momentum before collision and after collision is 0. Then momentum would be perfectly conserved. 385 versus 0.385. But okay, so from only when mass 1 weighs 470 grams, then momentum would be conserved according to draft science model. Okay, so this would mean that the blob of clay would have to weigh 230 grams. Okay, so if it is true that cart 2 weighs 482 grams, and if it is true that cart 1 weighs 241 grams, then the mass of the blob of clay would have to be 230 grams, right? In order for momentum to be conserved in draft science model, given these timings, if these timings are correct, right? If these timings are correct, then yes. And if it is true that if cart 2 weighs 482 grams and cart 1 241 grams, then the blob of clay would have to weigh around 230 grams. So almost the blob of clay would almost weigh the same as the cart itself. Now that would be impressive. Now, what do we see? So cart 1 would have to weigh 470 grams. And cart 2 weighs 482 grams. Only difference of 12 grams. They almost weigh the same. Now, what do we know about elastic collisions of two carts weighing the same, equal masses? Well, Cart 1 comes to a full stop after collision. Okay, now this one only weighs 12 grams. This mass 1 now weighs 12 grams less than mass 2. Now, what would the reflection look like? It would have to be a very, very, very small reflection. And what do we see? Yeah. There we go. That's quite, well, that's my question. This reflection, if mass 1 weighs 470 grams and mass 2 weighs 482 grams, so only 12 grams heavier, would that produce this reflection? Would it produce this reflection? I would say no. Okay. The reflection would be a lot less. You ready? Okay, yeah. So again, according to draft science model, given these timings, cart 1 would have to weigh 470 grams if cart 2 weighs 482 grams. So only 12 grams difference. Would it produce this result? There we go. Would it create such a reflection like this? I mean, 470 grams versus 482, almost equal masses. We know that collisions between equal masses, all right, means that cart 1 will come to a full stop. Well, that's my question. Thanks for watching.